Okay, so in these problems, we're going to look at each of these rational functions. And remember, rational function is where you have a polynomial divided by a polynomial. And in each of those cases, that's what you see. So in letter B, you see a linear um, factor divided by a quadratic. So you have a polynomial divided by a polynomial. Even a constant is considered a polynomial. So you have a polynomial divided by a polynomial. So each of those cases, that's what you see. Okay? And so what you want to do is you want to determine the vertical asymptotes of, if any, exist for each of these. Now, one of the things that you've learned in a previous lesson was how to find the domain of a rational function. So in each of these cases, you could easily find the domain. So let's talk about that for a moment. And I'm going to use a separate sheet of paper to talk about finding the domain. All right, so the domain of a rational function, okay, the domain of a rational function is the values of x, or the domain. Um, so the domain of a rational function is the values of x. Remember, the x is the values in the domain for which the function is defined. Okay, so if you look at letter A, where we have f of x is equal to 3 divided by x plus 4. So remember, when you have a fraction, in this case a rational expression, rational function, when you have a fraction, it's undefined. It is undefined when the denominator is 0. So you want to find the values of x for which it is defined. Well, first of all, let's talk about where it is undefined. So a fraction is undefined when the denominator is 0. So all you do is you take that denominator, x plus 4, and you find out where it's equal to 0. That's all you do. So this is equal to 0 when x equals negative 4. So that means that the domain, and if you look at this on the number line and you put negative 4 and you cross it out, then the domain would be these two intervals right here. So it would be all real numbers except negative 4. So it would be the domain. So in set notation, so if you're asked to do this in set notation, you say the domain is a set of x's such that x does not equal negative 4. Oops, that should be a brace. If you're asked to put this in interval notation, the domain would be negative infinity to negative 4, parentheses because negative 4 is not in the domain, union negative 4 to infinity. Okay? Now, it turns out, now we got to be careful with what I'm about to say. Well, actually, I'm going to go ahead and find the domain of each, and then we'll come back and we'll do the asymptotes, the vertical asymptotes. All right, so that's the domain for part A. So all real numbers except negative 4, right? Okay, let's look at part B. All right, part B, we have g of x is equal to x plus 7 divided by x squared minus x minus 6. Now, again, to find the domain, all you do is look to see where the denominator is 0. Okay? Now, for us, the denominator will be factorable. See how this is quadratic? You can go ahead and factor this. So let's go ahead and rewrite it. So when I rewrite this and factor the denominator, I'm going to get x minus 3 times x plus 2. And so now to find the domain, I look at each of those factors and I set that equal to 0 because remember, you cannot have 0 in the denominator. So basically you're saying, where is x minus 3 times x plus 2 equal to 0? That's what you're asking yourself. Well, I have these two factors whose product is 0, so the 0 factor property says one of those has to be 0, right? And so when I set each equal to 0, I get x equal 3, x equal negative 2. And so in one of the videos you've learned maybe about a month ago or so, you then put those numbers on the number line just like this, and you cross them out because negative 2 and 3 cannot be part of the domain. And so then the domain would be those three intervals right here, those three intervals. And so So in terms of domain, if you write this in set notation, you would say the set of x's such that x does not equal -2 and 3, just like this. You write just like this. In terms of interval notation, you would say, now remember 3 intervals right here. You see that? 1, 2, 3. So you go from left to right. So you go from -infinity to -2, -infinity to -2 union, and then -2 to 3 union, and then 3 to infinity. All right, so that's how you found the domain. For C, we have this for C. So for C, you have h of x is equal to x plus 4 divided by x squared minus 4x minus 32. All right, and so when we factor the denominator, you always want to factor the denominator. You're going to get x plus 4 divided by, and when I factor this, I'm going to get x minus 8 times x plus 4. Okay, now be a little bit careful, and this is where this is going to be important when we talk about the asymptotes, vertical asymptotes. Remember, the domain is any real number, any real number for which the denominator is not equal to 0. All right, now be careful. If you go ahead and you reduce these right now, and you say the domain's all real numbers except 8, you're missing something here. All right, so even though you can factor that out, don't do that just yet. The factoring out is going to be important when we come to here. Okay, so you're going to see that in a little while. All right, but to talk about the domain, you set each of those equal to 0, just like we did with this one. So you have x minus 8 equals 0, x plus 4 equals 0. So x cannot equal, let me put it, x equal 8, x equal -4. So then the domain, I'm talking about the domain, so the domain would be the set of x's such that x does not equal -4, 8. Okay? All right, now let's go to D. So D looks like this. So here's D. So D is this function, k of x equals x divided by x times x plus 6. All right. Again, now notice the denominator is already factored for you. Don't reduce these just yet. If you reduce them, you're going to miss the domain. Your domain's not going to be correct. So don't factor anything out yet, or don't reduce anything out yet. And so we're going to set each of those equal to 0. X times x plus 6 equals 0. And then I set each of those factors equal to 0. So I get x equals 6, x plus 6 equals 0, so x equals -6. So then what I found is that the domain in set notation would be the set of x's such that x equals 0, does not equal 0, or -6. If you put this on the number line, here's -6, here's 0. We cross those out, and we look at these 3 intervals right here. So the domain would be from left to right, -infinity to -6, parentheses, because I cannot include -6 and 0, because that makes my denominator 0, which makes the rational expression undefined. Union -6 to 0, union 0 to infinity. And then finally, let's look at E. So E, we have h of x is equal to x plus 2 divided by x squared plus 9. Now, if you look at the denominator, again, it doesn't matter what happens in the numerator when finding the domain, right? It does not matter. It's the denominator. You don't want the denominator to be 0. But if you look at x squared plus 9, notice x squared plus 9 cannot be factored, right? And so if you think about x squared plus 9, if you think about x squared plus 9, where's it equal to 0? And you may say, well, I'm going to go ahead and get x squared by itself. That's fine. So when you do that, notice what happens. You get x squared equals a -9, right? But I want you to think about this. Anytime I square a number, that's always going to be positive or 0. Whenever I square a number, it will always be positive 0. Any negative number squared is positive. Any positive number squared is positive. 0 squared, 0. It's never negative. So x squared equal to -9 does not have a solution. So there's no solution, right? So what that means here is that there is no number, so no value of x will ever make the denominator 0. Okay, so no value of x will ever make the denominator 0. Um, and so therefore you would say that the domain, so that means the domain's all real numbers. So the domain would be, and in set notation, you would write there's a set of x's such that x is an element of the real numbers. And so we define real numbers as capital R. In interval notation, you say negative infinity to infinity. Okay? All right. Now that we reviewed the the idea of finding the domain of rational functions, let's go back and now talk about how do we find the vertical asymptotes of these rational functions. Okay? All right. Now, listen carefully. The vertical asymptote, to find the vertical asymptote, okay, to find the vertical asymptote, you're going to kind of do this in steps, and then we'll think about it. Number one, you're going to factor numerator and denominator. Okay? Factor numerator and denominator. Number two, reduce common factors. Reduce common factors. Number three, okay, so when I reduce the common factors, once you reduce the common factors, then set the denominator equal to 0. Okay? And solve for x. 4. The value of x is the vertical asymptote. Okay? The value of x is a vertical asymptote. All right, so it's very important when you find the vertical asymptotes that you factor numerator and denominator. When I found the domain, notice I said in many of the cases I said it does not matter what the numerator is when finding the domain. You are just looking at the denominator, and then you're finding out where's that denominator equal to 0. Okay. When we find the vertical asymptotes, you are now going to worry about the numerator and denominator. All right, and you're going to factor numerator and denominator. You can reduce any common factors, and then whatever is left, then you're going to set the denominator equal to 0, solve for x, and that value of x is your vertical asymptote. Okay? All right, so let's go and do number 1. Okay, so number 1, to find the vertical asymptote, we are going to factor numerator and denominator. Notice I cannot factor anything else. Okay, once you do that, then you take the denominator. Remember step 2 or step 3, set the denominator equal to 0 and solve for x. So x plus 4 equals 0, so x equals a negative 4, right? That number here is your vertical asymptote. So you're going to say vertical asymptote. Vertical asymptote. Remember, vertical asymptote is a vertical line, so make sure you say x equals. Don't just say negative 4. In other words, if you put in the blank just negative 4, you cannot get full credit. It's very important you remember that vertical asymptote is a vertical line, so you have to name it using an equation. So x equals negative 4, and that's it. Now, if you compare that with the domain, notice we got the same thing. X equals negative 4, right? All right, so the domain would be all real numbers except negative 4, right? And that's what you see here. And it turns out that this value of x that's not in the domain is also the vertical asymptote. All right, let's look at this one. Oh, and by the way, here's what the graph looks like, just to show you. So the vertical asymptote is x equals negative 4. Here's the graph of this rational function. A very rough sketch of it. So this is f of x equals 3 divided by x plus 4. So the vertical asymptote, we always denote it using a vertical line. See how, and we also name it using the equation of vertical line, x equals negative 4. And then you kind of plot some points using this expression to kind of help you with the sketch. When you get into calculus, you'll be able to do this a little bit better by using derivatives. But the graph always, well, I got to be careful. But the graph never crosses the vertical asymptote. Okay, never, ever, ever. So you'll notice it'll get close to it. So notice it'll go on this side like this side like this. And then for the most part, it won't cross the horizontal with a rational function. It won't cross the horizontal, but sometimes it does. Sometimes it does. Um, but this is what this one looks like. All right. Now remember when we did the exponentials, when we did the exponential functions, and so that's why you have to know what kind of function you're dealing with. With the exponentials, if we had an exponential, then the graph never touches the horizontal asymptote for an exponential. But with a rational function, sometimes it will cross it, and then it will kind of do this, and then come back and oscillate towards the asymptote. Okay. But that's what it looks like. Now, you're not going to be graphing this. All I'm interested in is for you to tell me what's the vertical asymptote. The vertical asymptote is x equal -4. If you were to graph it, it would look something like this. Okay? All right. But that's how you find it. You just determine what denominator. Well, I got to be careful. For this one, all we had to do was take the denominator equal to 0 and then solve for x. And that equation that you got here is your vertical asymptote. All right, let's look at this one. So the first thing you're going to do is you're going to factor numerator and denominator. I cannot factor the numerator further, so I'm going to rewrite it just like this. And then when I factor the denominator, I get x minus 3 times x plus 2. Okay. Now remember the next part. So that was number one. Number one says factor numerator and denominator. Number two says reduce. Okay, so now we're going to reduce if we can. Notice there's nothing to reduce. Okay. Number three says set the denominator to 0 and solve for x. So I'm going to set the denominator equals 0, x minus 3, x plus 2. It's already factored, so I'm going to use the zero factor property. X minus 3 equals 0, x plus 2 equals 0. And when I solve for x, I get x equals 3, x equals -2. And those are your vertical asymptotes. So your vertical asymptotes are x equals 3, comma, and then x equals -2. Make sure you say x equal, x equal. That's very important. Okay? So you got to say x equals 3, comma, x equals -2. And if you look at what we did when we found the domain, we got the same thing, didn't we? See right here? All right, so those are your vertical asymptotes. The domain would be all real numbers except these. Okay, and that's what you see here. All right. What the graph looks like is this. Now notice there are two vertical asymptotes, right? In number one there was one. In letter A. In letter B there are two. So here's what this one looks like. So you see you have two vertical asymptotes. This one is x equal 3. This is x equal -2. So notice you remember a while ago where we had the domain. You had this. Let me do it this way. You had this interval, this interval, this interval. So you had this piece, this piece, this piece. See that? That corresponds to this right here. So this piece right here, this part of the interval, -infinity to -2, that's what that graph looks like on that side. So the part of the graph looks like this. From let me get this back. From -2 to 3. Notice -2 to 3, the graph does something like this. You remember the graph never crosses the vertical. It never is going to cross the vertical. It gets closer and closer to it, just like this. And the same thing here, it gets closer and closer to the vertical asymptote, but doesn't cross it. And then for the third interval, remember there are three intervals here, from 3 to infinity, the graph does this. Okay? Goes towards the vertical, towards the horizontal. And in this particular case, it doesn't cross any of them. All right. So that was letter B. Okay. Now let's look at C. Okay, in C, let's go ahead and factor numerator and denominator. So in finding the vertical asymptotes, you have to factor numerator and denominator. The numerator is already factored. Cannot do anything else to it. The denominator, I'm going to get x minus 8 times x plus 4, just like this. Now, this time, remember when we did the domain? When we did the domain, I said don't, for the domain, I said, was this C? Yeah, for the domain, I said don't reduce, okay? And so for the domain, you not to reduce, because this function is not defined at two numbers, -4 and 8. But When finding the vertical asymptotes, you must reduce. You must reduce. So that becomes 1 divided by x minus 8. Okay? And now, we set the denominator equal to 0, and then we have one vertical asymptote. So the vertical asymptote is x equal negative 8. X equal negative 8. Now, what happens is this, just to let you know. So you see how the domain here was all real numbers except two values of x, and the vertical asymptote was only there was only one vertical asymptote. So that means that this negative 4, when x is negative 4, you're going to have a hole in the graph, H-O-L-E. So at x equal negative 4, there's going to be a hole in the graph. All right, so that's what that means. So when you reduce, that factor that's reduced produces a hole in the graph. It does not produce a vertical asymptote. It produces a hole. Okay. All right. So be careful. So when you studied domain, you did not factor. You had to set both those factors equal to 0, and then the domain will be all real numbers except those two values of x. When you find the vertical asymptotes, you must factor, because if you said the vertical asymptotes were both these two, that's incorrect, because the only one that's a vertical asymptote is x equal, that should be positive 8, sorry, positive 8. So the only one should be x equal positive 8. Okay? All right, so that was D. All right, let's look at actually C. All right, let's look at D. Okay, so the denominator is already factored, right? The denominator is already factored. So since I'm finding the vertical asymptotes, we're going to reduce. So reduce. So this becomes 1 divided by x plus 6. Then I take the denominator and I set it equal to 0. And when I set that equal to 0, I get x equal negative 6. And that is your vertical asymptote. So the vertical asymptote is x equal negative 6. All right, and remember when we did the domain, we didn't worry about reducing. Okay, all you have to do in finding the domain is set each of those equal to 0, and then the domain will be all real numbers except those two values. For the vertical asymptote, you have to reduce, and so the only thing left was this factor x plus 6, and that's what produces your vertical asymptote. So you may say, well, what about this value of x equals 0 here? That's going to be a hole. So there's going to be a hole at x equal 0. Whatever y is, when y is 0, you can figure it out. When x is 0, you get 1. So let's see where the hole is. So the hole is going to be at 0 comma x is 0, and then you always go back to the factored form here. So 0 plus 6 is 6, so you get 1 divided by 6. So you can get a hole in the graph at 0, 1, 6. That's what that means. Okay? All right. And let me just kind of real quick, and I'm doing this to fly here, but here's what the graph would look like for this one here, if you were to graph it right here. So it looks something like this. So you have a vertical asymptote at negative 6, x equal negative 6, so that's here, right? Vertical asymptote x equal negative 6. And you have a hole at 0, 1, 6. So at 0, 1, 6, which is, let's say, right here, there's a hole. There's a hole right here. So that's what that means. And remember, your graph oscillates towards, and also this is your horizontal asymptote. So there's your horizontal asymptote. So your graph goes towards these horizontal asymptotes, just like this. Okay. Notice, and on this side, let's see. Yeah, on this side, you're going to get something that this is negative 6, so it should be something like this. Okay. All right. So that's what the graph looks like. Now compare that one with one we had earlier. I just want to quickly show you. So with one that we had earlier, you see right here, there was no hole in the graph. None. Okay. The reason there's no hole in the graph was because we didn't reduce. There was no factors to reduce. Here, compare them. Okay, here, notice I reduced. All right, and so then the fact I reduced was x, which produced 0, and so there's a hole at at this is 0, 1, 6. There's a hole at 0, 1, 6. That's what it looks like. So that's what it means to have a hole in the graph. Okay. All right. Now you don't have to be able to graph this. You just have to be able to tell me the domain. But to state the domain, you have to remember you have not the domain. You have to find the vertical asymptote. You just have to find the vertical asymptote. To find the vertical asymptote, you have to remember to reduce. Okay. If you don't reduce, like you did when finding the domain, when finding the domain, you did not reduce. So you got two values of x that's not in the domain. But for the vertical asymptote, you have to reduce. So the only one that gave you a vertical asymptote was this one. This one produced a whole vertical asymptote. Okay? All right. Now, look at this one. So remember when we did this one, I cannot factor the denominator. That's the sum of two squares. So you remember the sum of two squares cannot be factored. So there's nothing to do here in terms of factoring. Okay? Now, you got to ask yourself, where is x squared plus 9 equal to 0? Okay? Well, x squared plus 9, so you may say, well, I'm going to get x squared by itself. That's fine. You get this. And you're going to say, well, I'm going to take the square root of both sides. Okay, that's true. All right, you can do that, plus or minus. But you got to remember, be careful, because some of you had a habit of saying the square root of negative 9 is 3. It's not. Remember, the square root of negative 9 is 3i. So you get plus or minus 3i, which is not a real number. So you get x equal plus or minus 3i, which is not a real number. So what that means when you go back here, right here, when you go back here, x squared equal negative 9, there is no real number for which x squared equals negative 9. There's no real number x for which x squared equals negative 9. So what that means is that the domain, remember the domain is all real numbers. All right? And in terms of vertical asymptotes, that means that there is no vertical asymptote. No vertical asymptote. So remember the directions said, find the vertical asymptotes if any exist. So this is one where it doesn't exist. So there's no vertical asymptote. And that's all you do. Now let's just quickly show you what the graph looks like for that one. For this one, and notice I didn't plot any points at all, but this is what the graph looks like. So this was h of x equal x plus 2 divided by x squared plus 9. So notice there's no vertical asymptotes at all. You don't see any. And notice a horizontal asymptote is, and you don't have to worry about the horizontal asymptote. So don't if you don't know how to find the horizontal asymptote, don't worry about it. All the direction says is what's the vertical. Okay, that's all I'm interested in. What's the vertical? And I just wanted to remind you that there is a relationship between the vertical asymptotes and the domain. It's not exactly the same. You see that now, especially with something like this, right, where you have to reduce, but there is a relationship between the domain and the vertical asymptote. All right, but for this one, there's none. So you just notice that this is a situation where the graph crossed the horizontal asymptote right here. It crossed it right here, and then it crosses it, and it comes back, and it goes back towards the horizontal asymptote. It doesn't keep going down, okay? See, there's a horizontal asymptote, so it crosses it, and then comes back and goes towards the asymptote. All right, but that's how it looks. All right, so that's it. That is how you find the vertical asymptotes. Just remember though, when finding vertical asymptotes, you're gonna don't just set the denominator equals 0. You gotta reduce first. Reduce first, and then whatever's left, that's what you set equals 0, and that becomes the vertical asymptote. All right. Okay, so that is it. Do the best you can. Hopefully, this kind of made some sense for you in terms of vertical asymptotes and the relation between vertical asymptotes and domain. All right, so that is it. That is it for this part of the lesson.